Alright, welcome back. In this video, we're going to go over some MyLab examples from section 9.2, infinite limits and limits at infinity. Okay, so for this question, we want to write an equation for the line that goes through the point -5 and 3, and it's horizontal. So let's first graph it to take a look at the point that we're given. So -5, so that's our x value, and 3 is our y value. So I have this point right here, -5 and 3. And so I want a horizontal line, which means that it goes left to right, and it has to go through this point. So my line may look like this. Okay. And so a horizontal line takes the form of y equal to a number, because this is my y-axis, this is my x-axis. Okay, so this value should be 3, because no matter what x value I put in, let's say 1, I should get 3 out, right? This is 1, 3. Say I chose this value, -3, I should still get 3 out. So that is why y is equal to 3 is our horizontal line. So now we want a vertical line. So let's graph again. Let's put the point on -3 is my x coordinate, and then -9 is my y. 5, 6, 7, 8, 9, barely down there. But now instead of a horizontal line which goes left to right and intercepts the y-axis, I want a vertical line, and this goes up and down, like so. And so now you can see now that we intersect the x-axis, and so the equation of our line, our vertical line, will be x equals -3, because no matter what my x is, no matter what my y is, my x is always going to be -3. So at this point, let's call it 2. I have -3, 2. Let's pick this point. I think that's -5. So I have the point -3, -5, and then this point down here, which we were given. So notice how all of these are in the x, and they're all -3. So that's why we have this equation for this line. Okay, so for this problem, we are concerned about a limit as x goes to infinity of f of x. We don't really know what f of x is, but that's okay because we have a graph on the right. So for this limit, we want to know what happens to my function when my x gets really, really large. And graphically, that means if I'm tracing along the function and I continue past the graph and on to the right, my x values are like 10, 12, 14, all the way out to like 1,000,000 and so on, right? Out to infinity. What is my function doing? So if we look at the graph, it seems that it's reaching this like steady state where it's kind of leveling off at this value of -1. It's kind of hard to see, but we are just 1 unit down from the x-axis. So that's why our answer will be -1. Now, if we look at this question, it's a little different where we have a graph of f of x, and now we are approaching -3 from the right. So as we've done before, let's trace along the graph from right to left. All right, we're still not at -3, so I'm going to keep tracing. I'm going to keep tracing right to left. And now I'm getting really close to -3. And I want to ask myself, what is my function doing? And it seems that if it just keeps continuing on to infinity, it looks like it's just going to keep getting more negative and smaller. So we write this as -infinity. Okay, so that's what's happening to my y value. So this, if we continue the axis, this would be -11, maybe -100, -1,000,000, all the way out to -infinity and beyond. Okay. Alright, so for this problem, we want to find the limit of this function that we're given. We no longer have a graph. So let's find the limit as x approaches 4 from the left of 4x minus 4 over x minus 4 squared. Okay, so the first thing you should always do is try and plug in this value. Okay, so let's do 4 times 4 minus 4 over 4 minus 4 squared. So I'm already seeing something that I don't really like. So 4 minus 4 is 0, and 0 squared is still 0. And in mathematics, we can't divide by 0, so that's a problem. But another way we can think of it is, let's say we found the limit for minus 4x. So now let's say we instead substitute in 4, and then because we're coming from the left, we want to put in something like much smaller than 4. All right, so 4 from the left. I'm just keeping that sign there to remind me that it's not exactly 4, but it's something just a little less than, so like 3.99999. Same thing for here. I'm going to put in 4 with a little minus sign just to remind me that that's what we're doing. So we can look at it now as the numerator will be 4 times 3.99999, which will still be a positive number, almost 16, very close to 16. So our numerator will be positive. So that's something to think about. And then our denominator. So now we're thinking about 3.99999 minus 4. So that's going to be a really small decimal, almost 0. Okay, so if we multiply that, it's going to be, if we square that, it's going to be an even smaller number, like even smaller. So when we divide a really small number that's almost 0, okay, so if we divide a positive number by a really small number that's almost 0, okay, that's going to blow up, all right? So if you divide something by a really small number in general, it's going to be a bigger number. So that's why this is going to be infinity. Now, if that was a little too conceptual for you, you can always graph these functions or try finding certain points. You can definitely do that as well. So if you have Desmos or a graphing calculator handy, or you know what this function looks like, you can always look at a graph. I'm a very visual learner, so I like to take a look at things with a graph. So 4 from the right or the left, it looks like this, and from the right, it looks like that. So that's another way you can confirm your answers. Is always using a graphing calculator or utility. All right, so now let's look at what happens to the right. So I want the limit as x goes to 4 from the right of 4x minus 4x minus 4. Now again, if I try to plug in 4, we'd still get this divide by 0 problem. So that's not good. But I can now write 4 times 4 plus, and this symbolizes a number like 4.000001, like very close to 4, and then minus 4. And then again, down here, I'm gonna put my 4 plus, and then put minus 4. So 4 plus, that's not an actual number. We're just speaking conceptually, but it's just there to remind you that it's not exactly 4. So we don't encounter this divide by 0 issue. So my numerator, 4 times 4 and a little bit of change would be about 16 again, minus 4. So we'll still come out with a number on top, which is good. So now let's look at the bottom. So if I were to subtract 4 from a number like 4.00001 minus 4, I would get 0.000001. Okay, and then if I square it, it even gets larger. I'm sorry, smaller. And like how we saw in the last one, if we find a really, really small number and divide a constant by that really small number, it's going to grow large. And that's why this second limit would be infinity. And now, once we did part A and B, all we have to do for C is ask ourselves, is A and B, the answers from A and B, are they equal? And they are, and so the answer to part C is also infinity. Right? And again, you can use the graphing calculator, find the graph looks like that, around 4. And so you can see as we approach 4 from the left, let's trace it. We go up, 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 and we continue growing without bound. So that's why it's infinity. And then if we trace it from the right towards 4, my function keeps going up, and also to infinity. Okay. So let's practice another one. So here we have the limit as x approaches 7 from the left of minus 7x minus 7 over x minus 7 to the 4th power. So again, if we try to plug in 7, we will definitely get into a little bit of an issue because this right here will lead us to a divide by 0 error. So we can't exactly plug in here. But again, if I think about plugging in a really, really small number that's close to 7, so maybe 6.99999, right? Then the top will be a number close to 49 minus 7, and my bottom, it will be negative 0.00001, and then let's say, and then if we raise it to the 4th power, it'd get even smaller and positive. So like maybe we'd have an answer like this. So it's a really, really small positive number. That's why we do 0 plus. And so a positive number divided by a small positive number will give us positive infinity. But let's remember our original function has a negative. So here our answer will be negative infinity. All right. And so we can play the same game for looking at the right hand limit at 7. So 7 plus. So again, plugging in will give you the divide by 0. But let's think about a number really close to 7 to the right. So that number could be 7.00001. And then if we think about the denominator, this was a really close number to 7 from the right. When we subtract 7, the difference would be this really small number, and then we raise it to the 4th power, so it gets even smaller. And so we essentially have the same problem as before. We have a positive number up here, a positive really small number, so it's going to blow up to positive infinity, but don't forget about the negative in front. So A is negative infinity, B is negative infinity, and for C, what do we have to ask ourselves? Is the left side limit equal to the right side limit? They are. And so the answer to C is also negative infinity. Okay, let's say you, for some reason, got infinity, like for a different function. So you have negative infinity here, but you have positive infinity there. So graphically, that would look like, so from the left, my function goes down to infinity, but from the right, my function goes to positive infinity. Then the overall limit would not exist. So just make sure that if you were to have an overall limit, then the right hand limit and the left hand limit has to be equal. But yes, and this graph, by the way, if you wanted to graph it, it looks something like this. So you can see from both directions as you approach 7, we go to negative infinity. All right. Okay, so now we're moving on to polynomials, and we want to talk about the leading term. So with polynomials, they'll always be in the form of x to some power a plus x to some other power b, and so on, and then maybe a constant c where the power is 0. Okay, so what you want to look for, the leading term would be which term has the highest degree or the power. So here, with the polynomial that we're given, we have p of x is equal to 12. So there is an x here, but it's raised to the 0 power, because anything raised to the 0 power is 1. So you can kind of write that in there if that helps. X to the 6 minus 8x to the 7th. So now the leading term would be the term with the highest power, and that would be this term. Okay. So let's write that here. So minus 8x to the 7th power. Okay, so now we want to know, what is the limit? The limit of p of x as x goes to infinity. So the reason why they asked you what the leading term was in A is that the leading term basically means that when x gets really large, or when x gets really large in the negative direction, that term will overtake the function, and it will be the primary indicator of what will happen. Because let's think about p of x. So if I put a really large number here, so remember that this is just 12. So if I put a really large number in for x, so let's say maybe like 1,000,000. So then I would have 1,000,000 to the 6th power. Okay, so that's gonna be ginormous, just absolutely huge, times this 5. Okay, and then I have this minus 8 times 1,000,000 to the 7th, which is basically taking this number and multiplying it by 1 more million, right? Because it has the difference in the degrees is just 1, so you're just multiplying 1,000,000 one more time. So this term is going to be even larger than this term. right? So that's why it's the leading term, because it's just going to absolutely overpower the other terms. And so that's why we can look at that term to determine what end behavior of the function is. So the limit of p of x, you can really just say that it's about, or it's equal to the limit as x goes to infinity of the leading term. All right, so if we put in a really large number, infinity, and we raise it to the 7th power, it's going to get very large. This is going to be very large, infinity, and then just watch for the negative here. So our limit will be negative infinity. Okay, so now let's look at what happens if I put in negative infinity. So if I want the limit as x goes to negative infinity, I still can use this leading term that we got from part A, so minus 8. All right, so let's try plugging in a really large but negative number. So negative 8, let's say negative infinity, not a real number, but we can think about it in that sense. So if we have a really large negative number and we raise it to the 7th power, my sign of that even larger number will be negative, because odd powers don't change the negative, but even powers will change the negative. That's why like negative 2 squared will make 4, but negative 2 cubed will make negative 8. So just be aware of those algebra concepts. All right, so I have a negative infinity here times a negative 8. So a negative times negative gives me a positive, and that's why my answer will be positive infinity. Okay, so let's now look at some asymptotes. We have this function f of x equals 5x over x plus 1. So for horizontal asymptotes, you want to look at, if it's a rational function, you want to look at the degree of the leading term. So here they are understood ones, implicit ones, right? So I could write f of x as 5x to the 1 power, x to the 1 power. So because these degrees are the same, all I need to do is just say that the horizontal asymptote is this fraction, which is 5, right? You just take the 5 over 1, and that's 5. And let's remember, a horizontal line would cross the y-axis. This is an asymptote now, so it would look like this if you were graphing a function. Okay. So our line should be y equals 5. Now let's look at the vertical asymptotes. Now for vertical asymptotes, you have to think to yourself, can my denominator of this rational function ever be 0? So all you have to do is just solve where the denominator is equal to 0. And so we find that x equals negative 2. So graphically, we have this vertical asymptote here. And our answer is x equals negative 2. Let's try another one. For finding horizontal asymptotes, remember we want to look at the leading terms and their degrees. So degrees are the same. So I'm just going to take the fraction of their coefficients, which are an implicit 1, right? So I'm just going to take 1 over 1, which is 1. And so my y is equal to 1 as my horizontal asymptote. And then again, for the vertical asymptotes, we look at where the denominator is equal to 0. So x squared minus 16 is equal to 0. So x squared is equal to 0. And x squared, when I square root both sides, I have to add the plus or minus, which should give me 2 roots. Okay. Now, when you do vertical asymptotes and you see that it's a rational function, you should also see if the numerator is factorable. Because if it is, then it could potentially cancel out with some of the terms in the denominator. So the numerator is not factorable here, but let's just say plus 6, oh sorry, that would be plus 4x minus 4 because it's a difference of squares. But let's say I had a numerator now of x minus 4. And so you notice that this term is the same as this term. So we can cancel them. And so that would only leave me with an x equals negative 4 as the vertical asymptote. So always be sure to check if the numerator is factorable, because it potentially could cancel out with some of the terms in the denominator, which would remove one of your vertical asymptotes. But for the sake of this problem, the answer is negative 4 and 4. Okay, so I think this is the second to last objective, if I'm not wrong, but we are going to talk about the end behavior of this function. Okay, so we have, so we have the limit as x goes to infinity of 42x fifth plus squared over 18x to the fourth minus 3x. Okay, so for this one, remember when we were talking about the leading terms? Well, it's coming back, okay? So for this one, you want to do the same kind of analysis, right? So if you plug in infinity, you're going to get 42 infinity to the fifth plus 3 times infinity to the squared over 18 infinity to the fourth minus 3 infinity. So you don't know whether the numerator or the denominator grows faster, right? Which is going to be bigger. So that's kind of hard to tell, but we can use the leading term to determine what my limit is. So I want to find the leading term of my numerator, and between the 2 degrees, I have 5 and 2, my leading term would be this 42x to the fifth. All right, and in the denominator, I have a choice between 4 and 1, this implied 1, and so my 4 wins, this 18x to the fourth term. Okay, so now it's all a matter of the limit as x goes to infinity of 42x to the fifth over 18x to the fourth. And we know from our properties that we can pull this out. This is a constant, right? So we can just pull 42/18 out. I'm not even sure what that is, but let's pull it out of the limit to infinity. And then we're left with x to the fifth, x to the fourth. And because we're taking the limits, we can do the cancellation. Limit as x goes to infinity. So if I cancel x to the fourth with 4 of these x's, I'm left with x. And so the limit as x gets really large of x will be infinity. All right, you have this 42 over 18 multiplied, but infinity kind of captures that. Okay, so this answer is infinity. Okay, so let's play a similar game here. So if I try to plug in infinity, which again, not a concrete number, but let's just think about it theoretically. Oops. So I can't tell whether the numerator is going to be greater than the denominator. But what I can tell is my leading terms from these, the numerator and the denominator, right? So my leading term for the numerator would be the 6x, right? And for the denominator, my leading term would be 5x. Because remember, over here, this 4 really is x, but to the 0th power. Same for this 2. And this has the power of 1, so 1 is larger than 0, so that's why these two are my leading terms for the numerator and the denominator. So now let's go ahead and just worry about our leading terms. Okay, and so if we can pull that constant out. Here's my constant. So let me pull out 6/5 of the limit as x goes to infinity. I have x over x. And so this equals 6/5 limit as x goes to infinity. We can cross out these x's because we're talking about limits. So this is the limit of 1, which is a constant function, as x gets really large. Because there is no x here, our limit would be 1. And then don't forget about this constant out here being multiplied. And so our answer here would be 6/5. Alrighty, so let's do 2 application problems and then we'll be done for this section. So here we have a company which they're planning to manufacture snowboards. They have these fixed costs of $400 per day and then total costs of $5,800 per day. That makes 20 boards. So for part A, we want to find this cost per day function that's linear related to the output per day for 1 board. So notice how we have this $5,800 for 20 boards, but I want to model what the price is for 1 board. So all I'm going to do is do 558 over 20. I'm going to divide by that 20, and I'm going to get 270 for 1 board. And so my function, my c of x, will be 400. So that's my base price. That does not change regardless of how many boards I sell. And then now I want to add in my price for 1 board. So that's 270x, whereas x is the number of boards I sell. So now for part B, we want to find the average cost per board. And so they tell you here that the average cost per board is our c of x function that we got from A divided by x. So all we do is just divide 400 plus 270x over by x, and you can rewrite it as 400 over x plus 270. And that is your average cost per board function. In part C, we're looking to graph this average cost function, so that's this part. All right, so we have this 400 over x plus 270. So one thing you can do is you can plug in numbers if it'll help you. So let's put in x and then my c of x, my c average of x. Okay, so if I put in, let's put in 1, because I can't divide by 0, so can't put 0, but let's do 1. So 1 would be 400 over 1, which is 400, plus 270, so that would give me 670. And then if I wanted 2, I would do 400 divided by 2, so that's 200, plus 270, which would give me 470. So all I'm doing is I'm plugging in this x value into my average cost function. I'm gonna skip to 400. I'm sorry, 4. Divide 400 by 4, that's 100. So I'm gonna get 370. Let's do one more. Let's do 5. If I divide 400 by 5, I get 80. And 80 plus 270 would give me 350, I believe. All right, so we can kind of see this trend where we started out high at 670, and then as my x gets really large or larger, we notice that it's starting to decrease and almost taper off, perhaps, and that's kind of suggested by the graph options you have. So let's find the ones. Okay, so you notice on the axis it starts at 1, so that's why you can't see 600 on this graph, so just keep the scale in mind. All right, so that's good. So 2, we want to be around 470, so I'm assuming this is 100, is that 2, 3, 4? Okay, and then, yeah, this might be hard to tell, but 2 might be around here, so that's potentially right. Okay. But if we thought about it using limits, let's see what happens to my end behavior. Let's think about limit as x goes to infinity of my average cost function. Plus 270. Okay. So if I plug in infinity, I get 400 over infinity plus 270. Let me erase that. Okay, so if we take a positive number and we divide it by a really, really, really large number, that's gonna go towards 0. And so this term is basically gonna drop out for really large values of x. And so that's why when we did this point analysis, we noticed that the numbers are starting to slow down. Like they're still getting smaller, but the difference is getting smaller, almost reaching a steady state, which we might see in the next question. But anyway, so the limit of this function is 270 because this term again goes to 0. And so we're left with 270. And so you can look at this graph and try to figure out which one has an asymptote, because a horizontal asymptote would suggest that we are reaching that steady state in the end behavior. So let's see, this is 100. So this one is definitely a good contender, right? Because this horizontal asymptote's in between 200 and 300. So it's probably going to be A, but let's check out the others. This one, 100, so that's right at 200, so probably not it. 100, 200, 300, again, probably not it. And then this one is at 400, so A is our correct answer. And again, we can verify because we know that the limit as x gets really large, goes on to infinity, of our average cost function is 270. And so what that means is as I'm tracing along left to right and I'm going all the way out to infinity, it's just going to continue approaching 270. It's never going to cross, but it's approaching that. And so that's why A is correct. And we might have already answered this question inadvertently, but this question is basically saying, what is the average cost per board tending to go towards as production increases? And production increase, that means as my x gets really large. So I kind of talked about this before, but the limit as x goes to infinity of 400 over x plus 270, right? A really large number, or a constant number divided by a really large number will tend towards 0, making it drop out. And so we are left with 270, and that will be your answer for this part. Okay, let's do one more quick application problem. We have this population of a culture of tumor cells given by this function p of t. We are first trying to find the limit of this function as t gets really large. which I imagine t means time. So as time goes on, how does the population of this culture of cells behave? So if we do limit as t goes to infinity of 3300 t over t plus 6. So think back to a few questions ago, all right, when we were talking about leading terms, right? So I can plug in infinity if you want. It might be easier to tell which grows faster, but might not be, right? So which one grows faster, we don't know. But if we only considered the leading terms, it might be easier to tell. So my leading terms here would be my 3300t, because that has a degree of 1, it's the only term in the numerator. And in the denominator, I have t to the 1 power, and then 6t to the 0th power. So my t is my leading term for the denominator. And so we can rewrite this problem as the limit as t goes to infinity of 3300 t over t. And so let's use those properties of limits. Let's pull that constant out, that 3300. Okay, a limit t goes to infinity, and we're left with this t over t. We are allowed to cancel here because we are talking about limits. So we are left with 3300 limit as t goes to infinity of 1. And the limit of a constant is itself. So we get 3300 times 1, or just 3300. All right. And so this last question is just interpreting what we just found. And basically, steady state is just the number that we approach if we just go on and on and on to infinity. So I'm not exactly sure what it looks like, but as x grows, we know we're gonna go and approach whatever p of t looks like. Sorry, this is p of t. Okay, so as x gets really large and we keep going out, it's gonna approach but never cross that 3300, and that's why it's called a steady state. It's just gonna hang out there, keep approaching, but not doing anything interesting. So our answer is A. Alrighty, well, thanks for watching this video with me and doing the problem. I hope this prepares you well for the 9.2 assessment, and I'll see you in 9.3.